So we're going to continue with techniques of integration. Spotlight myself. Okay, so we're going to continue with techniques of integration up till now. Oops, why does that look weird? One second. There we go. Okay, so we're going to continue with techniques of integration. Up till now, let's see what we've talked about. We've learned integration by parts. We've learned trigonometric integrals. Last time we talked about trigonometric substitution. Okay, so the whole idea here is that, let's just remind ourselves, let's go to writing mode. Crap, where's writing mode? There we go. Okay, so remember the whole idea is that every derivative rule, so if the derivative of big F equals little f, every derivative rule can be rewritten as an integration rule. Okay, so if you have a derivative rule, you can turn that into an integration rule to then find the antiderivative. So let's like write this down the steps. All right, so derivative rule becomes integration rule, and then that allows you to find the antiderivative. Why do we care about finding the antiderivative? Well, because if you're evaluating a definite integral, the easiest way to evaluate the definite integral is if you know the antiderivative, right? Using the fundamental theorem of calculus. Okay. So this is like the easiest way to do this. Okay, and then there's a horrible way that generally no one wants to have to deal with. You could take the limit of the Riemann sum. Be written like this. Okay, this would be called the numerical method. It's what computers do. It's called numeric integration. Interestingly enough, did you know that computers were, like the modern computers were sort of invented to do numerical integration? Does anyone know what problems they were solving? Like, there's some cool history here. Like, computers were invented more or less to do this. If you even go back to George Boole's difference machine, the difference machine was basically created to calculate integrals. That was like in the 1840s. But there was another guy, his name was von Neumann. Does anyone know what von Neumann was working on? That he created like the ENIAC and the JOHNNIAC and all those like UNIVAC, all those early computers in like the 1930s and 40s. Anyone? No, not to find prime numbers. Although he did end up using it to do that, but that's not like why people paid the big bucks. Turing and von Neumann, more or less together, like invented the modern computer. What problem was Turing working on? Yeah, it was related to war. That's how Western society works. Like, war funds a lot of shit, a lot of scientific. Yeah, to solve Enigma. So Turing, they made something called the Manchester Baby came afterwards, but Turing's first computer was created to solve Enigma. Does anyone know what von Neumann was working on? So that's one war connection. What about von Neumann's computer? What was he working on? Or people connected to him? So we got one of them. If you've watched the movie The Imitation Game, they talk about this a little. So for von Neumann, they were working on something called the implosion problem. Does anyone know what the implosion problem is? Actually, it was von Neumann and another guy named, starts with a U, Ulam, and Teller. Has anyone heard of the implosion problem? No? No one's heard of the implosion problem? I'm so sad. Does everyone know what an atomic bomb is? I'm assuming yes. We've all heard of atomic bombs. Does anyone know how atomic bombs work? Like, how do you get that big explosion to happen? Like, what's the process? Are people like Googling it right now? Brian looks like he could be Googling. I can tell because you're like, we're like looking in, you're like, interest. Yes, the Manhattan Project was the project to create the atomic bomb, but keep looking. What is the implosion problem? Flooding is another related thing. That is another thing, but not the implosion problem. That what you're talking about is true. They were afraid that when they blew up the atomic bomb, it would set off a chain reaction that would burn all the oxygen in the atmosphere, yes. So they were like pretty freaked out when they ran it. Well, I guess when it comes down to the atomic bomb, what is the principle that it uses, that it's based upon? Does anyone know? Should have learned this in like your chemistry classes. Yeah. So fission, nuclear fission, right? And like what Matthew put in the chat, you're compressing the center into a critical mass. So there's actually two ways to do an atomic bomb. So what are the two types of fissile material that are used in an atomic bomb? Does anyone know? What are the two materials? Yes, plutonium and uranium, P and U. So there's two ways. They had two theories about how to do the atomic bomb, which is why there was, what was it? What were the two bombs called? Was one of them Fat Boy and the other one was Little Man?
Little Boy.
Oh, was it Fat Man and Little Boy or Fat Boy and Little Man?
I think it's Fat Man and Little Boy.
Little Boy and Fat... Okay, I had it backwards.
Fat Boy.
Fat Boy and Little Man, yeah. My daughter's like laughing at me here like what did you think? So these are actually the two different Little Boy Fat Man. Yeah, so these are actually the two different designs. So one of them is an implosion design and the other is a gun design. So in the gun design, what you have is a bunch of uranium in a big ball. Or maybe plutonium, I don't remember. Let's just say it's uranium. And then what you do is you actually have a gun, a cannon, that shoots out plutonium. And then when the plutonium hits the uranium, right, it breaks it apart, starting the chain reaction. Okay? Now the other method is the implosion design, in which you had a shitload of uranium in a sphere, and then wrapped around that, you had a bunch of plutonium, like a plutonium shell, basically, wrapped around it. And then you basically had to shoot the plutonium into the uranium, and you did that by having a bunch of bombs around the plutonium, and when they exploded, that would cause the plutonium to implode into the uranium. So does it make sense? All this plutonium would collapse into the bomb. Now to do that, you needed to make sure that it collapsed all at the same time. And they actually invented computers to do the integration, to figure out like where you would need to put the charges to make this happen. And it was too hard to calculate that by hand, so what did they invent? They invented the computer. Which is sort of intense when you think about it. Like, the only reason we have computers are because... Basically, okay, like, does anyone know how much, like, those first computers cost? Like, in real terms, like, today? Like, not just to make the damn thing, but, like, to design it, too. Yeah, there was, like, $1 billion project. Yeah, it was like hundreds of millions to literally build the thing, and like billions to like for all the research and development. Like, who's just gonna randomly pay billions of dollars? Like, the only reason Turing and von Neumann and all these people were able to create this is because they were like, look, you're not gonna have a bomb unless you like give us like $1 billion to make this thing called a computer. I know you've never heard of it before. It's literally something we're inventing, and we hope it works. Peace. Thank you for the check. Can you imagine that? Like, there's probably stuff like that happening today. You know, where someone has some crazy idea and they're like, look, if you'd really like to solve your problem, I'm gonna need like $1 billion. Like the first computers were all handmade. It's pretty intense. You should like Google it. They had to like wire them all by hand. So anyways, they were invented to do all this stuff. It's pretty cool, which is like why so much money goes into STEM, right? Does it make sense that like, you know, we pay so much money for people to get STEM degrees because like the military industrial complex is more or less like we're pretty useful. Yeah, Oppenheimer was the dude who oversaw all of this. Like he was the dude who was like, he was a scientist. Like basically they needed a scientist who also was good at like running shit, like to oversee all of it. So Oppenheimer was a physicist at Berkeley and he knew all these people. Like he knew Teller, he knew Ulam, he knew von Neumann, he knew Turing. He knew a bunch of mathematicians and physicists, and his job was basically to recruit people. He was like, you know, someone would say like, look, I have this implosion idea, but to be honest, I don't know how to like put the charges to make it work. And then Oppenheimer, because he was like a pretty smart guy, was like, do you know what? There was this dude who was like working on this machine that would do a bunch of calculations for you automatically. Like, let's hire him and bring him into the project, right? And he just would do that over and over and over. So anyways, back to, you know, the applications of all this, because, you know, war pays for everything in our society. The easiest way to do this integration is if you have the fundamental theorem of calculus. If you can't find one of those, if you can't find an antiderivative, you have your numerical methods. But then there's some other tricky methods you use to find antiderivatives. Okay, so some of the methods we've learned so far are things like U substitution, integration by parts, what else have we got? Trig integrals. And then finally, trig substitution, which we did last time. Right? Remember last time the whole idea was like you had these functions which didn't look like they were trig integrals, but we did these special substitutions to turn them into trig integrals, and then we solved them using the techniques that we had learned last time. All right, so what I'm talking about here is, do you remember like solving the integrals like the a squared minus x squared sort of stuff? Do you remember how like we drew the triangle and we started noticing like, oh shoot, that's like the length of a hypotenuse or the length of a side or something like that, and then you're able to like turn that into a trig integral, which you solve using the previous methods. Has anyone watched a program? There's actually a really good show about the Manhattan Project that's like actually fairly scientifically accurate. Is it called Manhattan? Oh, yeah. I highly recommend this show to anyone who's like interested in just learning about it if you don't want to like read. It's like a pretty good dramatization of the whole thing. Oops, I'm going to put the link in the chat. It's a pretty good TV show in its own right. Very good drama. Scientifically accurate. Sort of. I mean, as far as like a TV show can be. Okay, so now we're going to learn a new... Shh, quiet. Shh. The dog's sitting there, he's like barking. Or he wants to bark. Now we're learning a new thing called partial fractions. This is actually a really old technique. Euler came up with it like in the 1700s. Yeah. It's been around forever. Okay, so let's talk about it. So, where does this idea come from? So it comes from the fact that what is the derivative of the natural logarithm? Yeah, 1 over x. Nice. So because the derivative of natural log is 1 over x, yeah, I know, you like beat him out by like just a moment. Because the derivative of natural log is 1 over x, the antiderivative of 1 over x is the natural log. Okay, which means that like, with U substitutions, you could solve some problems like this. Like, let's say you have x squared plus 1 on the bottom. Okay, so if you have like x squared plus 1 on the bottom, that could be your u. So if x squared plus 1 on the bottom is your u, what is your du going to be on the top? What would we like it to be? So like if your u is x squared plus 1, you're going to need to do u substitution. Well, not 1. Yeah, you're going to need a 2x dx. So if you have a 2x right here and then a dx right there, looking at this, you're like, oh shit, like x squared plus 1 is my u, and then 2x dx is my du, so let's just put a 1 right here and that whole thing is du. And then now you look at this and you're like, oh wow, this stuff here, I actually know what the antiderivative of this is, right? The antiderivative of 1 over x dx is natural log x. You're like, oh, my antiderivative is going to be the natural log of u plus c, right? And then if you substitute your u back in, you'll get the natural log of x squared plus 1 plus c. Boom. So because the antiderivative of 1 over a variable is just the natural log of that variable, we need a method to sort of make this happen. Like sometimes you can just u substitute and like you'll get what you want. Other times it's going to involve this process called partial fractions. Okay, so it's called partial fraction decomposition. So let me give you like an example. So did everyone see how my integral of 2x over x squared plus 1, it was really easy to do the u substitution to turn it into 1 over u? And then because I had the 1 over u, you just get the antiderivative natural log u. So I want to pause. Did that example make sense? Yeah, it's not fun. Okay, so here's like where you run into difficulties. Okay, so let's say that you have something like you want to find the antiderivative of 3x over x squared minus x minus 2 dx. So you're looking at this and you're like, huh, it looks like partial fractions could possibly work. If I said, I'm sorry, it looks like u substitution could work. You would set your u equal to x squared minus x minus 2. The real dead giveaway here is that the degree of the bottom is 1 lower than the degree of the top. So you're looking at this, you're like, oh, if my u is x squared minus x minus 2, well, my du, what is that going to be? My du is going to be 2x minus 1 dx, right? And we are so close to being able to make the u substitution, but what's the problem? Like, what went wrong? Yeah, that minus 1 term, right? Does it make sense? You're like, oh, well, I have my 3x dx, which is just this part of it, right? You have this extra minus 1 here because of that negative x right there, and you're like, crap, like I can't just substitute it now. Like, it's in the way, right? So partial fractions is a way of dealing with this problem. Partial fractions deals with this problem. That we have the extra constant term in the differential. Because it's keeping us from being able to do our u substitution. And that's what we're like upset about, basically. Alright, so let's talk about how you do this. Okay, so what you're going to do is break up the fraction. So let's just like work with the inside. We've got 3x over x squared minus x minus 2, which in this case is 3x over x squared minus x minus 2 factors into x minus 2 x plus 1, right? Yeah. So we're looking at this and we're like, hey, do you know what would be really nice? If I can split this up into two fractions, where I have some a, where I have x minus 2 here, and some b over x plus 1. Because if you were integrating these, if a and b were just numbers and you were integrating them, what could you now do? So if a and b are some constants or numbers, like if a over x plus 2 plus b over x plus, if a over x minus 2 plus b over x plus 1 is equal to 3x over x squared minus x. Yeah, you can u sub with those denominators, exactly. You would look at this and you'd be like, oh, u equals x minus 2, which means my du is going to be equal to dx. You can factor out the a, and the same thing over here. Your u will be equal to x plus 1, which means your du will be equal to dx. You just factor out the b, and then boom, you'll get the natural log of x minus 2 and the natural log of x plus 1. Okay, so we need a method to break this into this for us. So that's what partial fractions is. So really what we have going on here is we're just solving a system of equations. So we're starting off with 3x over x minus 2 times x plus 1 equals a over x minus 2 plus b over x plus 1, and we want to know what a and b are equal to. So the easiest way to solve this is you take your equation and we'll multiply by x minus 2 times x plus 1 on both sides. Here, let's move all this over. I don't have enough space. Okay, so what happens on the left-hand side? Both of those cancel, right? Leaving you just with 3x. Now on the right-hand side, when you distribute, do you see how one of the terms is gonna cancel each time? Which means you're gonna be left with a times x plus 1 plus b times x minus 2. So as you get the term that you didn't start with. Okay. And then it's like pretty straightforward to figure out what a and b are. You can isolate the terms. By choosing x values. Like for instance, if x equals -1, what's going to happen? So why did I choose x equals -1? Yeah, to take away a. Because if x equals -1, you get 3 times -1 equals a times -1 plus 1. Right? And then this is going to become 0. The a term goes away. And then you get b times negative 1 minus 2. So what do we get here? We get negative 3 equals negative 3b, which means that b equals 1. Okay, then now we can use this. Why don't we, so we'll assume that b equals 1. And then we'll just plug in, I don't know, x equals 0. So you'll get 3 times 0 plus a, 3 times 0 equals a times 0 plus 1 plus, what was our b? 1. And then 0 minus 2, which means you get 0 equals, 0 equals a plus negative 2. So what is a equal to? 2. And then bam! Now you can solve the problem, right? Because what you've done is you've done a partial fraction decomposition. We now know that 3x over, what was it? X squared minus x minus 2 is actually the same exact thing as 2 over, what a is over x minus 2. 2 over x minus 2 plus 1 over x plus 1. And why are we doing this? Because now we can integrate the partial fractions with u substitution, thus finding me my antiderivative. Why did I choose 0 to plug? Well, it's just easier. It's just easy to plug in x equals 0, right? Does it make sense? Like 0 is an easy number to plug in. You just need to plug in some number other than the number you started with. I chose x equals negative 1 because it would get rid of the a term to solve for b. And then I just chose to plug in 0 because it's just easy to plug in 0. No special reason. Does that answer your question? It's a good question though. So just you should probably make a note to yourself. There is a reason for this. The reason for x equals 1 is that it gets rid of the a term. Whereas with this one, there is no reason other than convenience. Isn't there a way to do this? Yes, there is a way to do that. Because you can always turn. So what you could do is you could like, oh man, like it's not that difficult. What you would need to do is like you could split this up into 2 different equations by subtracting away terms, I believe. Because I know like every singular equation and 2 unknowns can be turned into 2 equations and 1 unknown. So yes, but I don't remember off the top of my head how to do it because I don't like doing it that way. Okay, so we're going to explore this whole idea of doing partial fractions and then using u sub to solve everything. Okay, so let's talk about like how the, or should I wait here a little longer? Are people still writing? Just don't want to go ahead if people are still working on it. Okay, so I can move on? Cool. Okay, so there's some rules for how to do partial fraction decomposition. Let's talk about it. Okay, so you're always going to be starting off with like, you're going to be integrating and it's going to be a fraction. So you're going to have p of x over q of x dx. So does it make sense? P is always going to refer to the numerator. Q is going to refer to the denominator. Okay, now what we're going to assume is that q of x can be factored, and it factors a particular way. And it factors into what are called linear factors. So it's going to factor into something like a1x plus b times a2x plus b times b plus b2 dot 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 all the way up to like anx plus bn. So these here, they're called linear factors. Right, does it make sense that each of the n is a linear? This doesn't always happen. Example, let's say you have x squared plus 1 times x minus 3. Right, do you see how one of these is a non-linear factor? Because like x squared plus 1, it doesn't factor, right? Because it has imaginary solutions. So does it make sense that this is not what I'm talking about? So the method we're about to discuss would not work for this. Okay, we'll talk about what to do later for that. Is everyone on board with that? Like, this method I'm about to show you will only work if the bottom polynomial factors into linear terms. Is the first one a1x plus b1? Did you not put a 1 there because it's understood? Oh no, I just forgot. I fucked up. It's a good catch though. Okay. So, interesting thing. If your denominator can be factored this way, then it is possible for your p of x over q of x to have a partial fraction decomposition, and what you'll set up is a1, which is a constant, over a1 x plus b1 plus a2, which will be a constant, over a2x plus b2 plus all the way up to your last one, which will be an over anx plus bn. These ai are constants. It's actually really interesting because Euler figured this out, but they didn't know why this was possible. If you're wondering, like, how are you supposed to know if it's possible to do this sort of factorization? There's actually a whole study of that, and it's called the study of abstract algebra of polynomial rings or fields. And there are things called factorization theorems. So there's like a whole branch of mathematics that's devoted to like, how do you know that this actually will break up like this? So does that sort of make sense? Like they figured out this trick like 300 years ago, and then people were like, why the fuck is it that you can always do this sort of partial fraction decomposition? Well, basically people like thought about that for about 200 years, and then eventually they were able to like prove and say why like this actually happens. If you're interested in this sort of stuff, this would be like a 3rd or 4th year level math course if you were like a math degree. An interesting thing, because this stuff like this is used so much in engineering, more and more, like a lot of engineers and graduate programs have to take that level of math. So because you need to understand like why these things work. So like, does that make sense? That's just a historical cool side note about like what's going on here. Like there are fields of study about like why this actually works. We're not going to talk about that in this class though. All right. Bueno so far? Shall we do an example of something like this? Yeah, cool. Okay, so let's do an example. So, yes, Taylor series be counted. So the whole point of Taylor series is actually, there's something called the Stone-Weierstrass theorem, which actually shows that you can come up with an arbitrarily complex polynomial that will fit any smooth function. So yeah, there's a whole connection in that branch of study. Taylor series is basically how you would turn some non-polynomial function into a polynomial. So like as a quick example, like sine, that's not a polynomial, but it is possible to find a polynomial that's as close to sine as you want, and it's connected to what you're asking about now. Alright, so let's do an example. Let's say that you were integrating 3x plus 2 over x cubed minus x squared minus 2x. So you look at this and you notice like, oh, I can't do u substitution because if my u was x cubed minus x squared minus 2x, that what would your du have to be? 3x squared minus 2x minus 2 dx. And you're like, oh, well, I've got a 3x and a 2. That's pretty close to those, but then like nothing there on top, right? So you couldn't do a u substitution as given. So you're like, okay, but I do notice that my p of x, which is 3x plus 2, and my q of x, which is x cubed minus x squared minus 2 of x, you're like, well, what can I factor that into? Well, first of all, I can factor out an x, and I'll get x times x squared minus x minus 2. Okay, which then can also be factored. X squared minus x minus 2. Didn't we encounter that in the last problem? Yeah, so we know what the factorization of that is. It's x minus 2 times x plus 1. And you look at this and it's the sort of factors I was talking about, right? X is 1 times x plus 0. X minus 2 is 1 times x minus 2, and x plus 1 is 1 times x plus 1. Right? Does that make sense? That's your aix plus b. Each of these terms looks like that. The x might not look like it, but it is, right? It's 1 times x plus 0. So you're like, oh shit, my q of x is factors into these linear terms. Yeah. So the factorization theorem tells you... Oh, what just happened? It's like stuck. Oh crap, I'm trying to scroll down, but it's like scrolling with me. Oh, what happens? Okay, this is not good. Oh, there. Okay. Yeah, I don't know why it was. I've never had that happen to me before. I was like, well, there's no point in scrolling. Like, it's scrolling with me. Okay. So, the factorization theorem now tells you that 3x plus 2 over x cubed minus x squared minus 2x can be partial fraction decomposed into a1 over, my first term will be x, plus a2 over x minus 2 plus a3 over x plus 1. Okay. So the way that you want to do this is you notice that this denominator on the left and the other denominators on the right, they are all the same, right? Because x cubed minus x squared minus 2x, these are the factors of it, right? So what you're going to do is you're going to take the right side and you're going to, what's it called? Common factor shit. I can't think of the terms. What's it called when you put fractions together and they all have different factors? I'm like trying to think of the words. Yeah, thank you. Yeah, there we go. So you want to put all those together and find that. So your LCD is literally x times x minus 2 times x plus 1. Because on the right-hand side, that's literally what that is, right? So the right-hand side, I already have that as my denominator. On the right-hand side, if you put them all together, they'll be equal. That's the same. Okay, so you're going to get a1 times x minus 2 times x plus 1. And then you're going to get plus a2 times x plus 1 times x. And then you're going to get plus a3 times x minus 2 times x. Okay, now, if these two fractions are equal, what will also be equal? To simplify things, we can like jettison some stuff. So like, do we necessarily even care about the denominators? Is my question. No, so we can get rid of them, right? Okay, so what we need to do now is we're just going to work on the top part. We're going to simplify it. Okay, so does it make sense? You're going to get a1, and then we need to multiply x minus 2 times x plus 1. If you multiply those out, you're going to get x squared minus x minus 2. Did I multiply x minus 2 and x plus 1 there properly? Yeah, because you're going to get minus 2x plus x, right? Yeah, cool. Okay, now you're going to do the same thing for the a2 term. If you multiply those together, you're going to get x squared plus x. And if you do that for the a3 term, you're going to get x squared minus 2x. Okay, so now what you notice is that you can gather, say, all of your x squareds. So does it make sense? You're going to have a1 times x squared plus a2 times x squared plus a3 times x squared, which means I can factor out, I'm going to have a1 plus a2 plus a3 times x squared. Okay. What am I going to have for my x terms? So do you see I'm going to have a1 times negative x? So that's going to give me a minus a1. The next term you have a2 plus x. That's going to be plus a2. Yeah, it's related to the other one. I just find this one's more useful to group by the x squared terms like this for this one. Because it's a lot harder to plug in x values to make stuff disappear. Okay, then what are you going to have for the x term for a3? You're going to have minus 2a3 x. Okay, then we have some constant terms. You're going to have a1 times negative 2. So let's just put those together. Minus 2a1. And then there are no other constant terms. Okay, now this is equal to the numerator on the other side, plus a2 plus a3x squared. Are there any x squareds from the numerator on the other side? So I'm going to set that equal to, or that's 0x squared plus 3x plus 2. Now these are two polynomials. And if these two polynomials are equal, what else have to be equal? I'm picking my nose. So like if two polynomials are equal, then their coefficients must be equal. Why is this important? Because it now tells me that a1 plus a2 plus a3 needs to be equal to 0, because 0 is the coefficient of x squared. What else also has to be true? Well, negative a1 plus a2 minus 2a3 needs to be equal to 3. And minus 2a1 needs to be equal to 2. Now this is a system of equations which we can now solve, and we'll solve by first getting that a1. We know that a1 is equal to negative 1. Victory so far, right? I've got one. One of them just falls right into place for me, right? And then we can just solve the other ones by leveraging that fact. If a1 equals negative 1, then a2 plus a3 will be equal to 1. And a2 minus 2a3 will be equal to... If you plug minus 1 into here, you'll get negative 1, which is positive 1. You'll have to subtract, you'll get equal to 2. Okay, now we can solve this by just subtracting. a2 minus a2, 0. a3 minus negative 2a3 will be a3 plus 2a3, which will be 3a3. 1 minus 2 is negative 1, which means a3 equals negative 1/3. Okay. And then now you can just plug in somewhere to solve the other one. Let's just plug all that into that. If you take those three pieces of information, you get negative 1 plus a2 minus 2 times negative 1/3 equals 3, which will be 1 plus a2 plus 2/3 equals 3. So what's 3 minus 1 minus 2/3? That's a 2 minus 2/3. 2 minus 2/3 is 1 1/3, which is 4/3. And now you have your partial fraction decomposition. Apparently, 3x plus 2 over x cubed minus x squared minus 2x is equal to, and we had this set up. Your first number is a1 over x, and our a1 was negative 1, so you get negative 1 over x plus a2, which is 4/3. So you're going to have a 4. And then you put the 3 on the bottom, right? Because it's 4/3. And then that was multiplied by, or that was on the bottom. It had x minus 2. Plus your a3, which is negative 1/3. So you're going to have minus 1 over 3. And then what did we have on the bottom? X plus 1. So yay! We have our partial fraction decomposition. Now, really, what is the whole point of this? It's because, well, now if you want to integrate this one, all you really need to do is integrate each of these, and why are we happy now? What method could we use to integrate each of those individually? Writing it down and I'm factoring out the constants. Yeah, you could do u substitution. So we're pleased with this because now I can just do u substitution on all of these. And in fact, what you end up getting, it's like really easy to look at this. You'll get minus the natural log of x, because you have a 1 over x dx, plus 4/3 the natural log of x minus 2 minus 1/3 natural log of x plus 1 plus c. Boom. This is the antiderivative of the original problem. What made it possible? U substitution. What made u substitution possible? Well, the fact that we're able to decompose the fraction, the original fraction, right? The partial fraction decomposition. Woo! Okay. How much longer do we have? Oh, we're like basically done, right? We're done. Wow. Today we actually went the whole time. It's pretty long. Yes, I'm gonna stop the recording.